All right. New chapter. Still talking about equilibrium. Okay? Still talking about equilibrium. This, though, applies specifically to acids and bases. The equilibrium with acids and bases. So we've got lecture 11 slides is this first set for chapter 14. And like I said, chapter 14 is a big chapter. It's a bitch, but it's also just a big chapter, right? Okay. So I need you guys to, on your own time, if you need to, refresh your memories of what we studied about acids and bases in Gen Chem 1, which was actually not a whole lot, really. We didn't really do a whole lot with acids and bases. We kind of covered these things. An acid, according to this Arrhenius definition that we've learned in Gen Chem 1, okay? What makes something an acid? An acid produces, what's this guy called? Hydrogen ion. In acid nomenclature, we might also call this H+ ion, we might just talk about it as a proton. Why a proton? Well, what is a hydrogen atom? 99.99% of the hydrogen atoms are an atom that has one proton and one electron and has no neutrons. There's a couple isotopes that do, but most of it doesn't have any neutrons. It's a proton and an electron. And if we're talking about an ion of hydrogen where there's no electron, then what is left? A proton. So sometimes in acid talk, when we talk about acids, we'll talk about acids produce a proton, an H+. Okay. Bases in this Arrhenius definition do what? The hydroxide ion. We need to know H+ and OH-, that's acid, that's base. But this is kind of a limited definition of what is an acid and a base. This is the Chem 1 definition. Okay, we're going to learn the Chem 2 definition. And then there's even more definitions after in higher level chemistries. But you also need to review, if you need to, how to name acids, because acids have their own rules about naming, don't they? HCl is, sometimes you can call it hydrogen chloride if it's in the gas phase, but if it's in a solution, if it's dissolved in something, it's called hydrochloric acid, yeah? I got a little sheet here that has not by any means all acids that you need to know, but these are very common acids. You should definitely recognize these names and these formulas. Okay. Do I have a paper to work with? Oh, a favorite acid to work with. Guys, I like acetic acid. And I love acetic acid. Not just because it's in vinegar and I love vinegar, because I do. Oh, yes. You know what I had at the ballpark last night? Pickle pop, frozen pickle juice, all that vinegar. Love it. Speaking of vinegar, speaking of acetic acid, we are going to work with that a whole lot in this chapter, but you need to review also from Gen Chem 1, guys. You absolutely had better know these 6 strong acids and the strong bases, because you had better remember what it means to be strong in this sense. Either one, to be a strong base or a strong acid. What does it mean? Strong acids are electrolytes, but weak acids can be electrolytes too. They're called weak electrolytes. What does it mean? Oh, okay, here's the word. Here's the word. The word is dissociates completely. Strong acids, bases completely do what? Dissociates. What's another word we sometimes say? ionizes. Okay. This chapter, equilibrium, is going to be about the weak acids and bases that do not 100% split. They only split a little bit. That's what this chapter is about. Okay. So that's a little bit of a review. Whew, 7 sections. Yeah, we doing all 7. Yep, we doing all 7. Okay. I want to get through Bronsted-Lowry acid bases today, and I'd like to start talking about pH and POH, and we'll just see how far we get. Okay, so here's section 1. Here's our new definition. Slightly more inclusive than Arrhenius. Okay. Bronsted-Lowry. So you can write this name down once, and then from then on you can just write BL. Okay. Now 14. We're in chapter 14. Bronsted-Lowry. Or capital B, capital L, acids and bases. Here's your basic definition. In this definition, an acid is a compound that donates a proton. What's a proton in our speak? When I say proton, we're talking about acids. I'm talking about it donates a H+ ion, right? Okay. Acids are compounds that donate H+ ions. And again, we will talk about this ion as a proton. We'll say that's donated a proton. Bases in this definition system are compounds that accept that proton. Like I said a second ago, strong acids and bases things like HCl, things like sulfuric acid, H2SO4, bases like sodium hydroxide, strong acids and bases dissociate, or the other word, again, we sometimes use is ionize. 100%. It's all split. Right? It's all split. Weak. How do you know if it's a weak acid or a weak base if you're looking at a formula? How do you know? Process of elimination. If it is not one of the 6 strong acids or the strong bases you are expected to know, then it's weak. Okay, weak acids and bases do something special. When I'm talking about them being in equilibrium, what they're really doing is an equilibrium reaction with water. Here's this word. Hydrolysis. So if I talk about give me the weak, so for weak acid, a lot of times I'll just write WA or WB for weak base. Okay? Give me the weak acid hydrolysis equation. Or I might talk about it as give me the weak acid ionization equation. Hydrolysis is ionization, but it's ionization that involves a water molecule, okay? I'm still going to be making ions here, but water is part of it. So again, here's my favorite acid, acetic acid. C2H3O2, acetic acid. What's in vinegar? Acetic acid forms solutions with water. Guys, pretty much all of our acid-base chemistry that we learn about in Gen Chem 1 and in Gen Chem 2 is water-based. In organic chemistry, you can learn an acid-base definition that is not water-based. We're not learning that. What happens in our bodies is water-based. What happens in a lot of chemical reactions is water-based. Water-based is by far the most prevalent. That's the one we learn first. So all of these acids and bases are what phase are they going to be? All of them are aqueous. They're all dissolved in water already, okay? Okay, but what about my water in this situation? What is water? Water is water. Water is liquid water. Do it.
What is that line underneath the weak acids? What is that? WA?
WA means weak acids. It's my abbreviation for weak acid. You didn't hear me say that? If I write WA, that's weak acid. If I write WB, weak base. Okay. No, I got you now. Weak acids. Weak acids. Weak. Not 100%. Not 100%. So it's in equilibrium. What does what in acid hydrolysis? Because this is what I'm looking at. This compound is the acid, right? Aren't I saying it's acetic acid? Isn't that what I'm saying it is? It is. According to this definition, what does an acid do? What is it that makes it be considered an acid? It has to donate a hydrogen ion. Which hydrogen ion does acetic acid donate? It's the first one. That's why I like writing the acetic acid formula this way. There's different ways it can be written. I don't care for those ways in Gen Chem class. I like this way. Y'all should do it this way. If you see a different way somewhere else, okay, ignore it. Do it this way. Where is this compound going to donate that H+2? Because it can't just go nowhere. It's got to go somewhere. What's it going to, you guys? It's got to go to the base. What's the only option I have on this equation right here? It's got to go to my water. This compound donates a proton to this compound. This is the definition of acids and bases. Now, so acetic acid is the acid. And in this situation, my water is acting as a what? Acting as a base. Because it does what? It is accepting the proton from something. Okay. What does that leave us with? What are my products? If this loses an H+, what is left over? C2H3O2. You guys are leaving something off of this, though. Okay, but you're leaving something else off of this. The charge. This is an ion. What is acetic acid made of? H+ ions and the acetate ion. And the acetate ion is C2H3O2 with a -1 charge. Okay. What's the other thing that gets made? So now I have H2O, but it's got an extra H in it, right? So the formula is not H2O, it's H3O. And this was neutral. It had no charge overall. And then I put an H plus with it. So now it's plus charged. And it's aqueous. And Joseph, I heard you saying it, this ion has a special name. Has a very special name that we have to know now. This is known as the hydronium ion. This is actually, when we talk about something being acidic or basic, when we talk about pH, what we're actually calculating is this concentration in the water. We're calculating the hydronium ion in the water. If you have an acidic solution, you put a compound in the water that's making a lot of hydronium ion, you're going to see that reflected in the pH value that we learned how to calculate. Okay. I just realized this this could come across as confusing, and I don't want it to. Strong acids and bases also do hydrolysis. So I just realized that maybe wasn't quite clear. They also do hydrolysis. It's just not an equilibrium. It's a 100%. Example. HCl. Okay. Aqueous. Right? When it goes into the water, it does the hydrolysis. It donates an H plus to the water. So we still have, this is my acid and the water is still my base. Only this is not an equilibrium. This is just a 100% forms what? What are the two ions that are going to get formed for this acid? Cl minus, chloride ion, right? And hydronium. Guys, it's the presence of the hydronium that means it's an acid, okay? That's really what's going on here. You got hydronium ion.
So it's always the first H.
Yep. The way we write, the way, and that's what you should go off of, for, I think, for now. Until you know more about, which we might do in this chapter. Can't really remember. Until you know a little bit more about which H it is, the first H. Okay. All right. So in Bronsted-Lowry definition, what we end up with when we do these hydrolysis, let me put a base one up and then tell you this term and then we're done. Okay. So that was a weak acid hydrolysis. That was a strong acid hydrolysis. Let's look at a weak base hydrolysis. Or again, you might see it called base ionization, right? Ionization. Here's your classic example. You should know, and love this one. Ready? This compound. What is the name of that compound? Very good. This is ammonia. Okay. This is ammonia. Ammonia. Okay.
Is the ammonia before?
Mm-hmm. Okay, so now I'm telling you guys, I'm telling you right now, I'm telling you this is a base. Okay, you already have this knowledge. Ready? Ammonia is a base. So where is the proton transfer happening? What's going on here? Yeah. If this is my base compound, and I'm telling you it is, then it has to be the one accepting the proton, right? Which means in this situation, water is acting as an acid. Water can be both an acid and a base. Absolutely, yes. Water is unique in that way. There's a word for that. We're going to talk more about it tomorrow. It's called amphoteric, but water can be both acid and base. Yes, absolutely. Okay. If this is weak, and I'm telling you it's weak, how do we know ammonia is a weak base? Because it is not one of the strong bases you are required to know. On that review slide at the beginning of these lectures, right? So it gets the double arrow. It's an equilibrium. What forms? NH4, because I'm gaining a hydrogen, right? And is it charged now? It gained an H plus. Sure is. Is this in water? Mm-hmm. It's aqueous. And what does that leave behind here? We're going to write an OH, and it is now negative because it lost its H plus, and we recognize that as the hydroxide ion, right? And so to leave you with today is this very important term that comes from this Bronsted-Lowry thing, something called conjugate acid base pairs. These are species that differ by one H plus in their formula. Show me in our very first equilibrium. Here's this weak acid. Where is, in this equation, where is its conjugate base? Where is the species that differs by one H plus in the formula from HC2H3O2? Isn't it this right here?
That's not a base.
That is a base. It's a conjugate base. It's a conjugate base.
The acid splits into conjugates.
The thing that differs by one H plus is its conjugate. If you have an acid to begin with, the other thing is then called the conjugate base. Here's my water, here's my H2O. What is it acting as in this reaction, in this equation? It's my base. What is the conjugate acid of H2O? Is this the conjugate acid of acetic acid? This is the conjugate acid of water. Is acetate ion the conjugate base of water? No. Acetate ion is the conjugate base of acetic acid. It's the conjugate base of hydrochloric acid. The chloride ion, right? Conjugate base. Where's the conjugate acid of water? Is H3O plus always the conjugate acid of water? Yes. Yes. Ammonia is a base. What is ammonia's conjugate acid? The NH4 plus. The thing that differs by one H plus. So what do we call NH4? It is the conjugate acid to ammonia, the base. What is the conjugate base of water? The hydroxide ion. See how we make those pairs? Super important in acid-base chemistry. These conjugate pairs are super important. So we got to know how to recognize them. Okay, so we'll start with some more of that tomorrow. Because it's at equilibrium, could I say it the opposite way? Absolutely. If I'm looking at NH4 plus and I say, what's the conjugate base of NH4 plus? Well, that's ammonia. Yep. Yep. Back and forth. Very good point, Scarlett. I like that. Good thinking. Okay. So that actually is pretty much section 1. I did finish, I think, section 1. We got some examples that we can practice first thing tomorrow, doing the pairs. And then we'll be ready to start section 2 and learn how to calculate pH and POH and stuff. So we're moving right along. Okay, you guys are not at all interested, I suspect, in me going ahead and opening up a homework for chapter 14. Okay, okay. And I'm not going to worry about opening this up today, but tomorrow I will open it up. She's a slow down. Yeah, I opened a few practice problems already for chapter 13. There was another one that there were some others that I was going through and making sure I didn't put accidentally extra hard ones in the practice sets. So. No, I'm talking about ones like where you had to solve an equation that had x to the 4th plus x cubed minus 2x. I'm talking about ones like that.
I mean, then you would just take out x.
I mean, you can do it, but it's not, well, and then what if you have a, you know, I mean, it's so.
No.
You got to try to factor it out and then set 1 to 0 and then just, yeah, and that's not what we're doing. So, okay, so we're going to go down there and we are going to pick up our experiment with centrifuging. Okay, I'll show you the centrifuge tubes. And the main thing, you guys, is all of y'all's solid has like settled down to the bottom, right? We got to shake it back up before we pour them in the centrifuge tubes. Okay. The solid needs to be suspended in the solution, right? It's not going to dissolve. It needs to be suspended so that when we pour it into our centrifuge tubes, we get solid in the tube. That's the goal. We got to have solid in the tube.
I believe we'll shake
it first before we pour it, okay?